Happy Monday. How's it going, everybody?
It's going well. Good to see you, Joe. Good to meet you, Laszlo.
Hey, thank you for having me, Joe and Matt.
Anytime. So yeah, on today's Monday morning data chat, we have Laszlo Sragner from straight out of London. For people who do not know who you are, do you want to give a quick intro?
Yeah, I have a background in finance. I worked for as a data scientist on Candy Crush. I was head of data science at a London fintech company for 4 years, built a team from scratch. Most of the experience, we are going to talk about here, is coming from my experience there. In the last 2 years, I run a consultancy called Hypergolic, which helps companies to get better at machine learning. I also run a blog, laszlo.substack.com, and please feel free to connect me on LinkedIn.
Nice. So so you said you were a data scientist for Candy Crush. Did I hear that correctly?
Yep.
Okay.
Yep.
That's now I'm very curious about that. Like, what was that experience like? I don't know how much you could say about
Did you used to be playing Candy Crush, Matt?
I never really played it, but my
I've never played it before. Yeah, I see everyone playing it. Yeah, what was that like?
Very addictive, right?
Yeah. And I specialize in virality and player behavior. So if you get those annoying, messages, that part was me. And also,
Thanks.
player behavior is a difficult concept, because essentially you need to analyze what the people think based on the data what you are having. And I think King was probably one of the first companies that had data at a scale that you can run experiments, which is like unparalleled. So that was an extremely interesting experience.
I'll tell you as an aside how I guess prevalent that game was. So I was at a checkpoint in the middle of Cambodia, and there were these soldiers with AKs and stuff, and I somehow didn't have my required. I don't have something that was required anyway. Long story short, they were too busy playing their Candy Crush game, so they kind of had to divvy out like who was going to go talk to the dumb American who forgot his thing. So they're more interested in that than probably taking some extra money from me, which I was happy to give. So yeah, congrats. That it's so sticky that in the middle of like one of the most impoverished countries in the world, they care about that more than they do about making a buck. So
this was all your fault, clearly.
Yeah,
no, I don't think so. I was a small cog in this mission.
That's cool. Yeah, that's awesome. So yeah, I mean, walk us through that. So you had a lot of experiences. Kind of leads us to today's topic. We're going to talk about data scientists need to write better code. I've seen your posts on LinkedIn, subscribe to your Substack, and see you in the ML ops community. And this is something that I know you're hammering really hard on. I mean, what were your experiences that led you to this point to think that data scientists need to write better code?
Yeah. I mean, this starts probably my quant finance background, where a lot of what we do as ML ops is just reinventing what the hedge fund was doing about 15 years ago. And some of the methodology and the way we think about what productionized machine learning means is coming from there. And obviously, the fintech I used to work for was started by MDs from Deutsche Bank, and they were expecting this kind of attention to detail from machine learning models that they were expecting at the show and the hedge funds they were working for. So it means that we need to like raise our level. So we were doing like production at industrial scale natural language processing. Natural language processing is not exactly a particularly industrialized subject, or at least at the time. And I was looking for techniques to how to improve our skills, and obviously we were suffering from tech debt. Things were too slow. We can't react. Especially you have a feedback, and then you were supposed to implement that into a model or a machine learning product or a business flow, and you can't. And the question is like, why? And like I was looking at the software engineers at the team, and they were like excellent programmers from Imperial and other Cambridge and other places, and I was wondering they don't have this problem. How come that they know something? And I started reading, like Codecraft. That's a big movement. Agility, extreme programming, pair programming, and all of these techniques of what is the essence, what is the substrate that makes them work, like the philosophy, and then how is it exactly implemented at the typing level. What do you need to do as a machine learning engineer, data scientist, to be able to unlock those capabilities or those kind of benefits that comes from clean code. And so that's where we started. And it took about a good couple of months until we get to the point where we started from scratch. So we essentially needed to attack every single problem of what kind of patterns are out there, what kind of paradigms out there, how can we actually implement that, put into production, and then see whether it works or not. Does it add value or not, or we should stop doing that. So we were writing unit tests for like months, and we didn't get anywhere. So because machine learning problems are not particularly suited for writing unit tests.
Right.
So usually what we do is like functional test, which means that run the entire pipeline on a diverse set of data, as small as possible, but still diverse, and then see whether it breaks. And that's one alternative of doing testing. So that was pretty much the origin where I started from, and slowly built up a body of knowledge, which is stripped down to the smallest amount of components to enable data science from zero to I know something, right?
And so it sounds like you're talking about basically shifting from unit testing to integration testing, more of an integration testing approach, but with, like you said, a reduced sample data set. And maybe you're almost thinking of that sample data set as being like a bunch of units. So you put in different types of data, malformed in various ways, and then you see, okay, does my pipeline handle this null? Does it exclude this null correctly? Does it join these two values together correctly? Does it handle maybe a repeated key correctly if I have some kind of like duplication?
Mm-hmm. Mm-hmm. I would be a bit wary about defining it at that low level. What we found is the largest problem in machine learning is analysis risk. You think that your model does something or your product does something, and it actually doesn't do it. And you should run one more query or one more analysis or one more notebook to figure out that it's actually something what you think is not true. And usually these are so subtle changes that if you have a bug at the level that would break a unit test, you will going to find it, you will be so off that it's going to be completely obvious. Because machine learning is always very statistical. Machine learning models are not correct from a rule-based way. It's always creating false positives, false negatives and whatever, that they are not defined by rules. There is no rules to check. And unit tests are very rule-based checking. It's like, I hope that this rule applies, which means that this goes in and this goes out, and this is a unit test, and that's very hard to create in machine learning. And this is what we found, that we ended up recreating deep learning models with NumPy, with random matrices and this kind of hacks, creating brittle tests when we try to solve this problem. So we ended up with this functional test, which is so one of our big paradigm is clean architecture, or you can call it plugin architecture or hexagonal architecture. These are all the same name. Essentially, you write your machine learning product as, let's say, an object, all right, like one class, okay, and then you plug in the external dependencies. And let's say the data source is an external dependency. You plug it in instead of, in production, it's a database. In evaluation, it's a file. In testing, it's an in-memory source, and that's where you can specify, as Matt suggested, a set of unit test-like samples that will hopefully break the code, the pipeline, if they are going in as they want. Obviously, this is a bit of like simplification. Often you can't do that. You end up storing in memory some kind of larger amount of data and push that through. But the goal is to be able to run the pipeline as fast as possible between two refactorings, because the key aspect of removing technical debt is refactoring. You need to have a way of changing your code and not changing its behavior. And that, like, there is no tech debt removal without this. And that's an extremely difficult situation to achieve in software engineering as well, in machine learning, it's particular because of the models, and current behaviors are absolutely not helping this. Neither machine learning lifecycle, orchestration, or any kind of stack-based paradigms are not helping you to say, I run the same code on my machine, run it, test it, and then I know that the same code we're going to ship, right? This is not in paradigm. Like currently, data scientists write something, and then the machine learning engineer rewrites it, right?
You can say something, Matt?
Oh yeah, I was going to say. So it seems like if you're talking about machine learning, there are kind of two different test practices here. So on the one hand, you need to be able to test the performance of the models after they're trained. So I expect certain behaviors based on the training set, but then there's this other problem of potentially testing the model trainer itself. And were you guys trying to do both of those, or was it mostly focused on like the trained model?
Very good point. This kind of testing is only for refactoring. So machine learning models as a performance cannot be tested in the sense that my new model is better than the old one. Like, does it have the same F1 score? I don't consider those relevant from an engineering perspective, because as I said, analysis risk is the most important risk in a model. So it means that you need to analyze your output as an analysis problem, not as an engineering problem. So all of our performance-based thinking or any kind of bug which are related to modeling errors are happening outside of an engineering testing. All right. Essentially, you need to look at the data.
So you mentioned the handoff earlier between data science and machine learning engineers. I guess, do you find that handoff to be acceptable? Well, let's start with that question.
No.
Okay.
No.
It was a softball, but okay.
Yeah. Too high. Yeah, essentially, that's one of our key, and I think this is what I mentioned as part of self-determination theory. That this is some of the key frustration that's happening in data science machine learning teams at the moment. Not like if you have two teams trying to solve a machine learning product separately, you are already in trouble. Usually these should be like somehow one unit where different skill sets come together. But largest problem is if you imagine like self-determination theory. What's the three components? Autonomy, mastery, relatedness. Autonomy, I influence the output. Mastery, while I am doing my job, I'm going to get better at it and it's going to be easier, right? And relatedness is that I make an impact, all right? So I make the difference. Now, what happens in a data science team where the data scientists work on the POCs and the machine learning engineers work on the product, right? So where is the autonomy broken down? Data scientists don't have impact on the output, all right? No, because the machine learning engineers making the models, right? The machine learning engineers are just following orders from the data scientists, so they don't have autonomy either, right? So you manage to create a situation where both of them feel frustrated by the other one. And where is mastery? You're not getting better at it because the data scientists collect the feedback from production in A/B tests or any kind of analysis. Machine learning engineers don't do analysis. There's a statistical problem. Data scientists are statisticians. The machine learning engineers are engineers. So machine learning engineers get input from these people. It's like we see these bugs and feedback, but we can't do anything about that because that's the data scientist job. So these are how these are breaking down, and all of this can be driven back that the data scientists are not trusted by the company or anyone writing good enough code that they can be shipped, right? And that's exactly where our paradigm says, especially in clean architecture, that the data scientists can work on abstract structures, and the machine learning engineers wrap this with the infrastructure, and the infrastructure is independent of the business problem that is getting solved. So the machine learning engineers can think of scalability, uptime, all of the MLOps prep and DevOps practices, and the data scientists ship their own code. So it means that if there is any kind of problem, they can fix it, and the same code goes into production. This is called by Google experimental operational symmetry, which is just a fancy name for same code runs everywhere. Testing, evaluation, production, or training.
This sounds like a really compelling idea. I mean, it's funny because throughout the tech industry, you see similar problems where there's a big wall between two parts of the tech business that need to work together. So, for example, another place where we see this all the time is software engineering and data engineering, where there's kind of this downstream attitude, like, I just throw it over the wall. You're supposed to take care of it. I'll change my schema. I don't have to communicate with you. That's all your problem. So we're big on that part of the stack. We're big advocates for, like, you just need more team integration, more communication. But in practice, it's always a challenge to implement this. And so for the similar paradigm with data scientists and machine learning engineers, like, in practice, how do you get those two teams working together? What are your thoughts on that? Like, how do you get them to sit down, communicate back and forth, make sure that everyone feels in control, writing clean code that can go into production? Like, how does that implementation process actually happen?
Yeah, you're completely right. The data engineering is and software engineering difference is the other key aspect. From a point of shared vision and like better communication, I don't really have a good process or rules or something which can be enforced, because if people don't want to work together, you can't do anything about them. But what we hope is, as here I mentioned, we start from quite a far back, like from psychology and why you are frustrated and do you want to do something about it, like some kind of therapy session, and hope that this is compelling to both of them, and then you can come in and as a force of a positive force and sell this to them, and then say, here is the point, what makes you frustrating, and this is the same thing, shake hands and it's going to be better. But otherwise, like, that's as old as technology, I think.
It's interesting. How did you come up with the insights to link like self-determination theory to burnout and data science? Because this is not an obvious link, right? Where I think the easy and probably subpar answer would be would be like, oh, let's obviously we just need better stacks or something like very superficial like this. But this is a very, I would say, subtle but useful insight. Like, what prompted this?
So King, when I worked for King, we were trained by game designers and company consultants who deal with this the psychological aspects of game creation, and that's a primary method. How do you formulate goals? Why do you keep playing a very hard game? Why do you enjoy it even if it's hard? And these kind of things what make you think. And then since then I use it everywhere. Like, I identify whether I'm going to do a hobby or not. Whether my kids are going to do their chores or homework or whatever. And here it was natural that when I was leading this team, I was thinking is like, are they happy? If you don't do the three components of self-determination theory, your team is going to be frustrated, and then you just move out these blockers from them, and then they will gonna, be happier. Like, especially like autonomy, just hand them autonomy, and they like, am I micromanaging them, and then when you recognize that, you stop doing it, then they're going to start being happier. But also there is like mastery. So you say, okay, someone just joined. Don't give them autonomy because they can't do anything with them. They want mastery. Start doing consciously look into them getting better at an early phase of the career, even if they are not like. If you are a junior at a new place, you're not going to be good at this. But you shouldn't expect them to be good at this, right? So we're going to cause them frustration that you expect them to have mastery, but why they still don't have it. So you need to train them, but then you can take away autonomy for a while, and to increase the pace of mastery. And this kind of thinking, and when we think about machine learning and MLOps, we say that we are too early in the technical cycle to be committed to technical solutions, right? So it means that the solution must be some kind of abstract first principle thinking until we have a very small set of things that we say, we absolutely must have this. We can't move forward this. And then we can start thinking about how to implement that into technology.
Sort of a related question here. George Vera kind of asks, how do we encourage data scientists to document their code? And I'll follow this up with when would you encourage data scientists to document their code? Early in what stage of their career would you start encouraging documentation? So we'll start with this question. So
that's a very good question. If you read like Clean Code or Refactoring by Martin Fowler, like these are like standard works. Documenting your code in the way that function X does X is not a very productive work. Your code to a certain extent needs to document itself. So that's one thing. It means that if you want to put effort into writing better code, that's your prime focus. Second, structuring your code is extremely important, and then writing like blog post style, an example style work is extremely important, especially if someone else is expected to use your code. Someone who doesn't have time or energy to go through your code base. Your team supposed to know how the code base is written, and they should refactor it as they go along to be easily understandable. Like that's one of the aspects of technical debt, is that it's easy to understand. It is easy to read, right? I said it in the other way around, but you get it. Yeah. So, like the sign of technical debt that you can't read your code easily, right? And that means that you can start refactoring it to make it easier readable. And obviously, some companies work like in packages, documentation. That's a different question, because you are essentially treating your users as an external company.
Right, you look like you have some thoughts.
I like this idea of literate code and making the code sort of self-documenting. I think comments are great when you need to clarify things. But yeah, in general, writing code where it's easy to read. I think it can be taken to extremes, and I might get in trouble for saying this, but like some of the paradigms I see in how SQL is written, I really don't like. I don't like it when people don't use Booleans for obvious Boolean logic, whether you're talking about code or SQL. I see stuff like that a lot where it's supposed to be more literate. But I think there are certainly things we can do as teams to come up with a set of coding standards where the code does kind of explain itself a bit more. And probably data scientists and machine learning engineers need to come up with their own paradigms within a company that are a bit different from what the software developers are doing, because they do have a different set of problems to solve, even if you have kind of a common base of how to do things. I think sometimes we have a problem in tech with like getting religiously attached to certain ways of expressing things. Like everything has to be absolutely this way. Mm-hmm. But I think you can come up with a set of best practices that the team kind of agrees on and commits to, and that evolves over time. So I don't know. What are your thoughts, Joe?
Yeah, I don't know. I mean, I think it seems in general the world of data and machine learning as well are borrowing a lot from software engineering, just because I mean, software engineering has been around for a long time and they've had enough room to do things wrong. So but it was there's an old tale of hand washing back in the day. Like that was something that I think when that was introduced back in the 1800s, doctors said that would take way too much time. So let's not do that.
Or flossing is another example you like to cite, right? Like who has time to floss?
Yeah, even though it's good hygiene. I mean, I'm curious, Laszlo, what are your thoughts on the basically the differences between tech debt and software engineering and ML?
Oh yeah, it's one of the problems with tech debt is everything became tech debt. It means that it's an excuse to have bad practices, and instead of the original meaning of tech debt. So the original meaning of tech debt is it's not even personal debt, because a lot of software engineers are not very good at finance. So the original metaphor of tech debt was corporate debt. let's build a factory from that and pay it back from the yield, But you do need to have, you can't just buy, because obviously credit card debt, you buy a TV, that's never gonna pay itself back, you just lost money. And this is why this is a metaphor is a bit broken, and we usually separate it, technical debt is well-maintained code, we make bets, and then sometimes they don't pay off, and then we can back out of them, right? And especially in machine learning, improperly structured code, it's usually destructive to change, and run an experiment, and then you lose connection to your previous versions. It's very hard to get back, especially retrain the model, things change, and then it's not particularly easy. And this is why we are advocating this kind of clean architecture, and then plug in where you are composing complicated behavior, and then you can run experiment by simply redeclaring your code or your product in a different way, and then executing that, and it's very easy to get back because you don't touch the original version of the code. Especially if you have like an A/B test, it's like an A/B test is it doesn't just run on a branch. Usually both versions need to be in production quality at the same time. This is an underreported aspect of A/B testing, and very hard to switch between them if you use destructive machine learning practices.
Emmanuel has a question here. Kind of going back to code documentation, how deep should data scientists document model and hypothesis assumptions embedded in the code? That's a really good question.
Usually what we there are like two, apart from the concrete code documentation, which we already talked about, there are two main points where I think that the data scientists are lacking the amount efforts. First is product documentation. Like product decisions, like how do you think about a business problem? What's your goals? What's the business context? What kind of data assets you have? Who do you need to talk to? And all of this, and have a rational, like it's almost like a blog post, or notes on a project. You're maintaining that as you are progressing with it from an ideation phase. Even from a not even a prototype phase. As you are thinking, this is a register of how you thought about that, what kind of meetings you had, and whatever. Let's call it product documentation. And connection to that is analysis, right? And that needs to be documented as you go along, recording what kind of hypotheses you came up with, and connecting them to, look at this web page, here is this, or this notebook, here are the results. This is why we choose these decisions, because this hypothesis came back negative. And I think that's not, like, often when you talk about documentation, you think about, it needs to look like SciPy's documentation, an incredible effort, like a Wikipedia for statistical methods. No, when you are creating a product, it should be a single page, record notes on your thoughts on this product, that someone can come in and pick up the thread when you are not available, right?
Interesting. Got another question here from Josh Wood. Excuse me. Hope my voice doesn't give out. As an MLE embedded with a team primarily consisting of data scientists, I can feel a bit overwhelmed trying to productionize several projects written in notebooks. The question is, how much should a data scientist understand about deployment engineering, maybe to reduce the delta between development and deployment?
Yeah, in our paradigm, data scientists work in VS Code. So like notebooks are for analysis. As I said, clean architecture, your product is a class, your model is a class, your data source is a class, everything is a class. You plug it together, and that's your product. If you plug in the production connections, then it's your deployed model. If you plug in the test data sources, then it's a test context. And therefore, when data scientists want to run an experiment, they essentially instantiate a product in their notebook, but the code itself is coming from VS Code. And you take this code and take it to the production, and you don't need to worry about it. And this is, I think, the key aspect of EOS is our experimental operational symmetry. Is that the data scientist writes the right code. They need to be able to write good enough code to, and that's not the case today. And this is exactly what we advocate: is to, you don't need to be a master DevOps engineer, because that's the alternative. Currently, when we say data scientists need to write better code, people think that, oh, you need to know Kubernetes, and it's like, that's not the same thing. It's an infrastructure principle that you use when you need to go productions. What you need to know is how do you structure your code, how do you write classes, how do you look at tech debt, and you identify code smells and stuff like that. This is a relatively easy to barrier to entry. And if you tell data scientists that they need to learn YAML and Kubernetes, then we're just going to resist this because they say it's too hard.
So in other words, for you, with this paradigm, they need to be writing code that can be run in containers later and run that locally, commit it, use Git, probably, put in pull requests to ML engineers so their code can be reviewed. But they really shouldn't be doing tasks like building containers or managing Kubernetes, which it's not just that it's hard. It's like that it's too much to do, right? It's too much to be good at all this stuff at the same time. You're not going to succeed. Okay.
I mean, let me ask you this. There's no shortage of data science courses, curricula, paths to learning data science. If you could, I guess, Laszlo, wave your magic wand and start over in the world, designing the perfect data science curriculum that would include code and other related things we've talked about, what would that look like?
Yeah. I mean, I can speak about our own
Sure. I mean,
course.
You built it. I guess you put some thought into it. So
yeah, which exactly does this. So it's incorporates these kind of paradigms. The psychological aspects, programming, training, code smells, how to write a single class, which is typical in machine learning, like usually data flow implemented in code. So that's one aspect. And what we found is the biggest problem in managing machine learning projects efficiently is decomposing problems and layers of abstraction. And I think this is what Matt was mentioning. Data scientists shouldn't write Docker containers. Yes, because these are different abstraction levels. Yep. Data scientists sometimes expected to speak with a business stakeholder or an abstract business problem, or a CEO, present some idea, and go back to their desk, write a notebook, and then write a Docker container. That goes from every single abstraction layer. That's not going to work. Like I understand that it would be great, and then there must be some people like this, and I'm sure Google can hire them. But in general, what you want is abstraction layers, and then at the top, that's where the data scientists talk to the business people, and then solve business problems, and then their work is wrapped by the machine learning engineers and put into production, and they can deal with the low level or the technical details. And what's the problem with decomposition is that in the current paradigm, as you are creating machine learning products, there is not too much room for decomposition, which means that all problems are your problems all the time. You're unable to create like bounded contexts and say, it's like, today I'm only focusing on this problem. Today I'm going to fix that data source that creates these incorrect data, but today I'm just going to focus on this one, and tomorrow I'm going to spoke to a stakeholder, get his feedback, and then I'm going to be able to. And this doesn't exist, and that this is our product management paradigm, but that is absolutely depends on having high quality coding practices, because these are, since the 90s, were designed to solve this problem, because 30 years ago, software engineers had the same problem. They had lack of abstraction and lack of bounded context or boundaries around any kind of context. And this is how behavior design and extreme programming was aroused.
Right. Yeah, and these aren't new concepts, like you say. I mean, like bounded context. I mean, that's an idea from early 2000s, right? Like this is, but a lot of these ideas, I mean, they're so relevant nowadays, and it's sort of the Lindy effect, I guess, with these sorts of ideas. They're good enough to be around, therefore they'll be around longer. But I remember when data science started taking off, around the world. I think it was Andrew Ng's Coursera class back in 2011, this machine learning course, it really, I think, kicked it off. That course alone, I think when it started, it had over 100,000 people in it. And that was pretty amazing for a free class. And it showed the interest. But what I also saw happening was it seemed like there was software engineering sort of doing its thing, adopting, principles that had, been percolating up for quite a while. Domain-driven design, you say extreme programming, DevOps had come onto the scene around, the late 2000s, and that was being adopted. But at the same time, data science was on the ascendance, and it was sort of this thing where people were trying to figure out what it was. There's Drew Conway's early Venn diagram of like stats, hacking, and domain expertise, or whatever it was. Maybe that was a definition of data science for a bit, but there was really no curriculum. So it felt like it was just sort of like things were tacked on. Like, oh, you need to learn Python, but yeah, what do I need to learn Python for? Or, you need to know R now, and that's it. Or both, actually, and Spark and all this other stuff. But what seemed to be missing was proper, I guess, software philosophy along the way, or even, as you say, decomposition philosophy, because it was really focused on how do I make a model. So it was a rush to make models, almost at the expense of all else. Because if I just get a model out, like that's kind of all that matters at the end of the day. So
I mean, part of the problem, I think, is like, first of all, most software engineering principles, this kind of craft, is not coming from academia. They are coming from like consultants in the early 90s, and then this is adopted. Like if you read the Pragmatic Engineer blog post, everyone is essentially doing XP now. So whatever they say, like they don't admit that they do agile, but they're essentially doing the same thing. They just name it differently, but that's not coming from academia. And I think that's like there are two driving forces which runs machine learning. And it's important that when we talk about these ML products, we are only talking about machine learning products. These are like automated business processes that are run independently. We're not talking about advanced analytics, which can use like an XGBoost or any kind of analytical techniques. That's a different question. And I think one of the biggest problems with data science is that this too is mixed. These are really different concepts, partly because analyses have a beginning. I get my data, and then an end. I hand in my data to the stakeholders, and then I can forget everything. The yield on the technical debt is not too high, because if I refactor my code, like, what do I win? Like, maybe I can make my next report faster, but from utility perspective, not. But in machine learning, that's a completely different. Like, some of these models are around for years, and the surrounding code is around for years. So this is a different perspective, and you need to separate in your head. And this is why we say it's like, oh, well, you say data scientists shouldn't use notebooks. It's like, no, they should use it for analysis, and only for analysis, because that is exactly what it is for, because you can do quickly a lot of things. When you find something, use VS Code to write it, right? And this is a bit made worse, because obviously all data scientists are coming from like either an analyst, they were data science analysts before, they were students because everyone is junior, and lastly, they were researchers in universities, which is the same, because they have an experimental problem and then they write a paper, hand it in, and then they can forget about it. That's the same, like beginning and end. And I think that all these forces ended up that data science is thought as something that has an end, and then you have a model, and then you hand it in, and then it's over. And this is exactly where our quant background came in, is that's not how hedge funds work, who trade models, because you never really remove your eyes from a model. You never really stop retraining and experimenting, trying to find out a better way to make money. So, and I think that's particularly our edge on the space, that we were not tainted by this kind of academic behavior.
So let me ask you this, though. Speaking of the interaction between academia and business, could that interaction be more productive somehow? I come from an academic background, and Joe and I both teach actually in the business school at the University of Utah. And so this is certainly a question that we're interested in. Like, are there ways that academia could be making better contributions or training students better? Because like you said, if these ideas, really critical organizational ideas of programming, like extreme programming, are not coming out of academia, what could academia be contributing, or how could they sort of get on the bandwagon?
Yeah, that's a very good point, because software engineers are complaining that CS students doesn't know how to write code. So
Yeah.
and it's a very craft based skill. You need to do it. If you do it 10 hours a day for 6 months, you're gonna be good at this, and you don't need to learn about electricity, whatever, like any kind of other subjects in whatever they teach you in computer science nowadays. But how yeah, it's very hard to pinpoint this, because especially in data science and machine learning, the subject needs to be taught somewhere. No one asks you, do you know how a support vector machine works in an interview, machine learning interview. This is why a lot of this kind of acing the data science interview is not right, because like I will gonna figure it out very quickly that you don't know how math works, in an interview. So you can't fake it. And I do think that their job is to drill this in. Like here is all the ideas from Bayes, linear algebra, deep learning, transformers, anything, information theory. It's like, fire hose, and then here is a paper. Now you can go and learn how to be a data scientist. But it is necessary, to know that.
Yeah, I mean, I feel like there are a lot of open questions here about that interaction. So for one thing, a couple of my friends who went to Stanford and went through the computer science department there, of course, that's one of the flagship computer science degrees in the United States for undergrads. But the complaint was like, okay, it's great that academics love Lisp, awesome, but like I took the Lisp class. It was very painful, but also I don't feel like it really helped my career that much. It's not like I had a much deeper understanding of how to be a good programmer after I took this class. And then on the corporate side, there's also this kind of academic focus in interviewing, right? Like there's this, you do these problems out of the algorithms class. Again, it's like, okay, does that really show that I know the craft of software engineering or not? And it feels like we have very similar issues in data science and machine learning and such, but maybe more so because these fields are newer than software engineering.
So. I don't really have a good answer to this. I do think that academic, like university studies, are partly an intellectual journey. You learn things that are not going to help you. It's like you maybe forget it, but as I'm sure you find it fascinating that Lisp actually works, or or anything around this. But I do think that what you actually use in practice is a smaller, more practical part. But why would I say that? In our previous company, the natural language processing models were knee deep in deep learning. We needed to learn every new papers, and the data scientists were not expected to not know how to do that. You're classified as a different type of employee if I give you a paper and you can't come back to me in an hour whether we should implement this or not. And I think that's especially if you are working in a high-end place, that's expected. But I can't just say half of machine learning course should forget about deep learning and they should teach code craft. That's not an answer.
That's interesting. It's something I've been wondering about too lately with I guess training for teams, really. And this is more of a just how do you train data teams and or software teams or whatever. But you look around, you do consulting, we do consulting. I mean, you go into a company, and I think the one thing you notice, and we notice, is skills and backgrounds are across the board. And I would say more often than not, outputs are kind of all over the board too. There's not really consistency in terms of how code's written. There's not really consistency in terms of even expectations or anything like that. What do you do you think that it would help to have like consistent trainings for data teams, for example, and best practices, code, et cetera, et cetera?
It's definitely it's somehow an adopted skill. So the team needs to somehow onboard this and then accept this as a positive force. And I do think that a struggling employee in a right context can have multiply their output. So it means that a lot of people are struggling because they never worked in a good team. Think about almost every machine learning team are burnt out. If you put somewhere in who is a bit below average, he's going to suffer because he's not going to get mentoring or any kind of help. But especially like this is why we emphasize in psychology and team spirit and how do you conduct a code review without actually pissing off each other, and what's important, what's not important. And I think Matt mentioned earlier that we software engineers can be like really dogmatic about rules, and that can lead to a lot of frustration, and it's actually not that important, not going to help you to make sure that every single variable is correctly named. It's not going to add too much value, but something else will gonna, and then and any kind of argument you have with your team about petty things is going to burn your credibility, and that's exactly, you need to show leadership and vision, and it's up to the leader of the team to raise up to this and execute. And the consultant, we consult that leader, so we are essentially coming in as an extension to head of data science, a tech lead in these teams, and then we coach them to that it's on you. This is a bad practice. You need to stop doing that. You can't tell that to your teams because they are juniors, and then they are going to struggle, and you're just going to tell them off. But I can tell to a senior leader that this is a bad practice. You need to change this.
Just got a question here from Smith. I think I'm pronouncing your name right. He asks, don't you think that striking a balance between corporate/academia is needed? The way you revisit your code is insightfully similar. Revisiting some of the math can be insightful as well, especially for ML practitioner, ?
Yeah, I mean, mathematical revision, like data science and machine learning is a quantitative subject. You, by definition, debug your math parts as well. And part of the reason why we are focusing on software engineering is because that actually helps you to move away from these problems. If you look at the data science team, what they do in the daily job, they fight their own code. What actually happens in high-performing data science team that has good quality code is that they have much more time for business problems, talking to business people, and conjuring up, new ideas in modeling, and then having a better thinking in terms of modeling, because they are not bogged down by tech debt. When a software engineering team has less tech debt, they can ship features faster. But your job is not to ship features faster. You need to have free time so you can do more analysis and more convoluted models.
Any thoughts on that, Matt? I mean, you come from a math background in academia, so I mean, what did you find the differences to be when you were working on theoretical math versus doing machine learning in the real world? Those are not the same things, by the way. Just saying.
No, they're not at all the same things. Yeah, it's an interesting question that I think we still don't have the answer to. And I feel like Europe and the United States are trying to attempt to attack these problems in a somewhat different way. And so far, like neither side of the Atlantic has really figured this out. I think in the US, we've tried to dramatically expand college education to a larger pool of people. And in the process, we've tried to make college education a bit more like vocational training. And I don't know that it's actually worked that well. Joe, you may have some opinions on this as well.
Oh, do I ever?
But it's kind of, it's very uneven how this is implemented. We kind of overpromise students what their education can deliver. Especially where maybe we're trying to bring in so many students. Some are landing in programs that are not quite as strong. So they're just not seeing they spend a ton of money in debt and come out of it without seeing a huge amount of value. At least in general, my impression is that the European and British systems are maybe a bit more oriented toward classical approaches to things, although maybe that has started to change as well. And I think you were alluding to this earlier, Laszlo, like there's general value to that just in terms of becoming an educated person. But again, it's not clear that we're actually preparing people to have successful careers by doing this. I think it works out for certain domains. I think Wall Street and, the London financial markets, they really like these people from these classical. It's almost like a class marker that you've come from this kind of education and gone into the system. And so, in the UK, it's like coming out of Oxbridge. In the US, it's maybe coming out of Harvard or something like this. But I don't know, in terms of actually building successful careers, I don't have answers. I feel like there's a lot of stuff we need to rethink, and we shouldn't be too attached to old paradigms. We should try to find things that are valuable in this kind of classical approach to education, but look at new approaches to things as well. And to your question specifically, Joe, about like coming from theoretical math, I feel like theoretical math these days is this very sort of classical discipline, right? On the one hand, that's hyper useful. Like I found teaching students to write good proofs is good preparation for them to think logically about code. On the other hand, we should also be directly teaching them to think logically about code within the code itself without like making it a strictly math subjects. I don't know what the balance is at this point. What are your thoughts on that? Any follow-on to that?
I don't know. I mean, I think as Laszlo says though too, and very correctly, it's not like the when you solve a proof, it's kind of solved, hopefully. Maybe not, but I mean, in theory. So, but machine learning, it's this thing that never stops. So it's as long as there's new data in the world, it should be a new model. So,
yeah. And one thing what we found is someone with a degree in machine learning probably can understand any kind of papers. The vast majority of, at least the popular ones, or distilled down to some kind of practical use. But it does take time to allocate that, and context switching is the worst enemy of that. And this is usually this is why a lot of machine learning teams are just like take a model, off the shelf model, train it on the data. Does it work? Doesn't, throw it, go to the next POC. And I think that a lot of the problem, and this is exactly why we are advocating good code, is because you are able to manage complexity and manage the process. And some of the machine learning problems that needs to be solved, like business problems, are just too hard for an average data science team to solve, with these techniques, And I think this is probably a fault of like Kaggle and the data science courses and data science teaching, is they say it's like, here is the data, here is the model, what's the best outcome, what's the F1 score, And then if it's too low, it's terrible, move on to the next one. But a business problem doesn't work like this. It means that the company has $100 million problem. It's like, here is all resources you can imagine, make it go away. If it can turn it into $100 million to a $50 million problem, a $10 million problem, you're going to be a king. How do you do that? Well, in every data science team, we're going to see we are not going to be able to do that, because the solution is so convoluted that we simply don't have any kind of paradigms or framework to frame this solution. And the available solutions, what we have, is simply the solution is not in this space.
Right. I guess I know this talk is about code, but what are your thoughts on automated machine learning, also called AutoML?
That's almost a trolling question.
It's not like I didn't expect.
Yeah. It's the same as maybe large language models or GPT-3 or DALL-E. It's like solving a problem is about intent. It's like the business tells me to solve this problem. I can't just outsource it to an algorithm, because the problem is going to be so convoluted that I need to make so many judgments and experiments in this process. It's like, it's not about F1 score. It's not like, okay, here is the data, and then there's a continuation of the Kaggle concept. Is like what you do is like auto Kaggle, isn't it? Like you just throw data to any kind of possible models, and it spits out the best F1 score. It's like we did this, and it was named entity recognition on Fortune 500 companies. And then we didn't do this test. So we just did it on all companies, all named entities in the world. And we have like a high performance one. My first question, my boss, was to, okay, list these companies by Fortune 100 by market capitalization, and then start checking the top companies' F1 scores by broken down. And he immediately spotted 3 spots. It's like he immediately, why is this broken? And it's like, you sit there train the model for 2 weeks, and then I have no idea. It's like, what? Like, I don't know. What can we do with it? It's like the top level performance is meaningless in a business problems, because there is always like multiple facets of your problem, and you need to, these are relevant questions. I can't just say to him, I don't know, because then we can close the company. So we went away, and then this is how this kind of clean code machine learning was born, because we needed to have a process that I can make an impactful change to the model that only changes, and that's going to be better. And that's exactly what we did.
These are very interesting points. Yeah, the fact that these automated machine learning systems are actually models that are like huge models that are trained on very generic data does create big problems. I think that also helps us to recognize their utility, right? So in general, I tell people that if they need to do machine vision, let's look at your machine vision application. Is it very generic? Do you just need to like recognize some basic shapes and objects within images? Then use Google's off-the-shelf model, right? That should work fine. But at the same time, I at one point in a past life worked with an online retail company that did a lot with furniture, and we tried to use one of those models. It was a complete disaster because we needed to know things like specific styles of couches and stuff. And that general purpose model, no matter how smart it wasn't going to know that information. It's like somehow expecting a really smart human to know all this stuff, right? All smart humans in general are actually very specialized, just like models. They like work in a career on very specific problems, and you wouldn't expect them to know something that's way, way out over here that's completely different.
Yeah. Exactly. Like there is nothing wrong with large models, like Hugging Faces models are just excellent, or Spaces models, but they. And these you immediately bring in analysis risk, because you are accepting someone else's assumptions, and now you need to test it to death, because you need to figure out that you haven't adopted some of their problems as well.
So I got a related question. It's sort of trolling, sort of not. What are your thoughts on GitHub Copilot?
Oh, here we go.
Laszlo's just going to leave.
I actually didn't use it, and I'm not sure. It's the same idea as some people say that it's freakishly, like they read their minds, and some people say that it's actually breaking this kind of cognitive loop of your typing. You are essentially ahead of your head, and your fingers try to catch up with you. But at the same point, it sometimes creates a wrong prediction, and it breaks this loop, and then you fell out of this kind of flow. And that's actually, we didn't speak about the flow, but that's an interesting concept as well. Is programmers are typically the people who experience flow, and I suspect that Copilot is a very, very good product to break this. And then fell out from this kind of subconscious level of problem solving. And then you need to trigger your conscious mind and delete, and then can induce some kind of frustrating. But I don't have experience with it, and I would not just tell it all. I'm sure so one day they're going to figure it out.
Interesting. Cool. I know we're coming up on the top of the hour here, so we'll wrap it up. I guess we can take a short question from Kosib if you have time. Should be a pretty quick one. Yes. How much of this lack of code quality is due to the use of Python? Kind of elaborates, duck typing and weak typing make Python easy to access, but it tends to result in code that don't obey solid principles and instead use other anti-patterns that are well understood in software engineering.
It's interesting, but I don't think our experience is that typing is not too important for machine learning code. And I don't have, like, I have this kind of theory that clean code should be not make you not dependent on typing, because the way the simplicity of the interfaces should reduce it to a certain point. And of course, machine learning is easier than software engineering, so you have less chance of creating problems that would affect static typing. And solid principles are not related to to typing. So this is the point of codecraft, is that you can write bad code, and that, like, solid principles and code smells are a discipline. You need to be disciplined to write, and this is why you have code reviews, because linting will going to figure out that you made an error, but the code review will tell you that the reader doesn't understand your code, and usually they don't understand your code, or you're creating technical debt. because you're writing your incorrect like anti-patterns.
Yeah, I think my opinion, it's not so much the language, it's how you use it. I mean, it's like any craft, really. I mean, a great software, craftsperson can write, I would say, the most elegant code and probably the quote crappiest language, just because they know how to write good code. So, yeah, I would say don't ever blame the language. I think that's
And just recently, I read a couple of very good articles on very simple ways to understand code, code quality issues, and there are very simple metrics like how many times it was changed and how long the file is, and that's it. And it's almost like you are done. You look at this and then start the refactoring there, and you will going to be ahead of yourself.
My other comment too would be a lot of code quality also comes down to using the right tool for the job, right? I mean, I think fundamentally Java is a great language in its own right, but it proved to be very awkward for trying to solve a lot of like data science and machine learning problems. Like it's just not the typing paradigm, like the static typing paradigm, and having to declare everything as a class proved to be very awkward for attacking those types of problems. And so maybe it's a combination of choosing the right language and the right tool set more generally, so packages and ecosystem, and then applying good coding principles, like you were saying, Joe.
I would push back on that, though. I mean, I think the first machine learning packages I came across back in the day were all Java based. Python was still considered a toy language at the time. I had, I talked to CS professors at the university who said Python was a toy language and it was not a real language. Actually, that's one person called it. It's called it crap, basically. You want to use a real language, use C or Java. But Java, the first when I was starting out in ML, it was Java. That was the language we had, and I think Python became popular because it was more accessible and easier to learn. I mean, and just basically because of that. Plus, I think libraries like Pandas really helped the way, way back in the day, where it made it a lot more accessible. It also made for some like really ugly code and data sets, but it did make it more accessible. And the thing, when you're in a hot new field like data science, the thing that you want is something that's going to accelerate adoption. And I think Pandas, Python, NumPy, SciPy did that, right? And then all the machine learning libraries gravitated towards Python. But back in the day, it was, I wasn't it before Python was that sounds like a hipster now, but anyway, I'll shut up.
So it's funny, like a lot of the early adopters in academia of Python that I knew were actually math people, and they were people who were really good at coding C, like topologists working these obscure areas, who would have to code, crazy types inside of C. And at some point they realized that they could integrate their C code with Python and their lives would get way, way easier. And so supposedly that was a big driver for uptake.
Yeah, that's interesting.
Maybe a last comment that if you have EOS, for example, so experimental operational symmetry, so I would recommend, and I heard that a lot of companies, especially like fraud detection and places where speed is critical, that their entire data science workflow is in Python, is in Go, because and they are quite successful with this. So it means that they can solve all of their problems in the same language, because that's crucial. Like this is what the first thing I learned in my job in 2005 when I joined this hedge fund, is that my boss said, it's like the model you write is the model we are going to trade on, and if you can't do that, you're not going to work here, That's it.
Pretty straightforward.
It's because otherwise they're going to be a translational issue, and that's more risky for the business than actually finding another guy instead of me who can create these models.
Wow. Well, at least you know where you stand. So it works or it doesn't. So that's pretty cool. Awesome. Great chat. Love having you on. Love to have you on again. For people who want to learn more about you, how would they do that?
Please reach out on LinkedIn and follow my blog.
Cool. What's your blog?
Laszlo.substack.com.
Nice.
LAS.
Nice. The first name Substack. It's awesome.
Yeah.
Cool. Very cool. Awesome. Well, thanks for being on the show. Thanks to the audience. Be sure and pick up our book, Fundamentals of Data Engineering, out on digital copy, out on O'Reilly and Kindle right now. Physical copies will be dropping in mid-July, I believe, mid-late July. So, thanks for your support so far. Book's killing it. It's #1 new release on Amazon in a number of categories. So, I think it blew away Matt and I's expectations by
yeah,
a shot.
We assumed that it would be kind of obscure, data engineering book when we started this. What was it? It was almost a year and a half ago, right? And yeah, seems to have kind of hit a nerve in some respects.
Yeah, but good. I think overall good praise so far. So we'll see how that goes. So
yeah.
Awesome, cool. Thanks, Laszlo. Thanks to the audience for great questions. This Friday we
Thank
have
you very much,
Josh.
guys. Goodbye.
Thank you. This was fun.
Yeah. This Friday we have Josh Tobin. He's from Gantry. He's going to be on talking about whatever Josh wants to talk about. He's a hyper smart guy, so good to have him on. We'll not be doing the Monday morning data chat next Monday because it's the 4th of July in the US. Apologies to Laszlo, who's over in the UK. And then coming back in the Monday morning data chat, I believe July 11th, we have Addy Pollock. So should be a good lineup. Hope everyone has a great week, and we'll talk to you all soon. So thanks.
Thank you very much, guys. Goodbye.
Thank you.